Hey folks, Ms. Gosling here. In this video, you're going to learn about nuclear binding energy. By the end of the video, you will be able to calculate the energy released during nuclear reactions. So with that, let's go ahead and get started. So we're going to start with something a little bit boring, and that is vocabulary. There are 5 key vocabulary words you're going to need for this topic and for this unit. So first of all, we're going to talk about binding energy. Binding energy is the energy required to keep the nucleons in the nucleus of an atom bonded together. So that's the energy that's keeping our nucleus from bursting apart. One reason we know that there needs to be energy involved there is it takes energy to move 2 positive charges together. So think about, and in order to create a nucleus, right, we're moving many positive charges together with all of our protons. So our next piece of vocabulary is mass defect. And mass defect is the total mass of the individual nucleons making up a nucleus. We know that that is going to be bigger than the mass of that nucleus. And the mass equivalent, and the mass defect is actually the mass equivalent of binding energy. And we're going to talk about how we go from mass defect to binding energy in this video. So the next thing we want to talk about is the binding energy per nucleon. So the total binding energy of a smaller atom is going to be lower than the total binding energy of a larger nucleus. And we know this because it's easier to bring two positive charges together than it is to bring 200 positive charges together. So a more useful term than binding energy is binding energy per nucleon, which is the total binding energy divided by the number of nucleons, or the number of protons plus the number of neutrons. Our last 2 vocab words are nuclear fusion and nuclear fission. So in nuclear fusion, 2 small nuclei bind together to create a larger nucleus. A good example of that is 2 hydrogen atoms combining to create deuterium. Our next example, our final vocab word is nuclear fission. This is one that you are that you've likely had a lot of experience with, and this is probably what you're most used to thinking about when you think about nuclear reactions. And in nuclear fission, one heavy nucleus is split into smaller ones. A good example of this is uranium-238 decaying into thorium and an alpha particle. So we see nuclear fusion happen in places like the sun and other stars, where light atoms like hydrogen are fused together to create eventually helium. We see nuclear fission happen in our nuclear power plants on Earth or in nuclear weapons. So with that, now that we have all of our vocab under control, let's talk about let's get into the nitty gritty, do some math. So we're going to start by talking about how we calculate our binding energy per nucleon. So we're going to start by determining the number of protons and the number of neutrons making up the atom. And you guys have done this in a chemistry class, but just a reminder, here's how we do it. So we're going to take, if we have, for example, uranium-238, atomic number 92, we know that uranium has 92 protons because the atomic number is the number of protons, and we know that it has 238 minus 92 neutrons. So what we're going to do is we're going to calculate the mass of our protons and our neutrons, and we're going to add that all together. So we're going to add the mass of 92 protons to the mass of 238 minus 92 neutrons. And just to simplify things, I'm going to write this as 146 neutrons because that's what it actually is. So what we're going to do then is we're going to subtract the mass that we find of our protons and our neutrons from the actual mass of a uranium nucleus. That is what that gives us our mass defect, because that's the mass of the mass of protons and neutrons that has been transformed into energy to keep that nucleus bound together. Next, we're going to use the equation E equals mc squared, which I am sure many of you have heard of, to calculate the binding energy. So in the equation E equals mc squared, for m, we're going to put in our mass defect, because that is the energy that has been turned into, or that is the mass that has been turned into energy. And we're going to multiply that by the speed of light, or 3 times 10 to the 8th meters per second squared. And that is going to give us the binding energy. Finally, we're going to divide the binding energy by the number of nucleons, which in our example is 238, to figure out the binding energy per nucleon, or the amount of energy used to keep each nucleon attached in firm to that nucleus. So with that, let's go ahead and do an example. The nuclear mass of helium-3, or He3.2, is 3.01603 U. And just so you're aware, we use U. So that U stands for atomic mass units. And 1 U is equal to 1.66 times 10 to the negative 27th kilograms. So the mass, so that's going to be our mass of helium. The mass of the proton is 1.00728 U, and the mass of the neutron is 1.00867 U. And we want to figure out the binding energy per nucleon for helium-3, or He3.2. So our givens are the mass of helium, which I'm just going to call little m, which is 3.01603 U. The mass of the proton, or MP, which is 1.00728 U. Just so you know, the mass of the proton can be found in your data booklet. And we know the mass of the neutron is 1.00867 U. We also know that 1 U is 1.66 times 10 to the negative 27th kilograms. And we know that C is 3 times 10 to the 8th meters per second. We also know that we have 2 protons, 1 neutron, for a total of 3 nucleons. And that, my friends, means that we're ready to write down our unknown, which is the binding energy per nucleon. So that brings us to the equation step. So to find the binding energy per nucleon, we need to start by calculating the mass defect. So mass defect, which I'm going to call delta M, is equal to the mass minus the number of protons, which I'm going to call P. So I'm going to say P equals 2 and N equals 1 neutron. So it's going to be equal to P times the mass of a proton plus the number of neutrons times the mass of a neutron. And that's going to equal our mass defect. Oh, excuse me, guys. I totally wrote that backwards. So it's going to equal the sum of the masses of our protons and neutrons. So the number of protons times the mass of a proton plus the number of neutrons times the mass of a neutron minus the actual mass of our atom. Then the second equation we're going to use is E equals mc squared to calculate our energy. And then we're going to divide that by the number of nucleons, so P plus N, to figure out our binding energy per nucleon. And instead of putting in our mass, of course, we're going to need to put in our mass defect. So delta M over the number of protons plus the number of neutrons. So combining our two equations together, we get the binding energy per nucleon is equal to delta M, which is P times the number of protons times the mass of a proton plus the number of neutrons times the mass of a neutron minus the total mass of our atom times c squared, the speed of light squared, over the number of protons plus the number of neutrons. And I want to mention, guys, you can solve this step by step. You can do this, and then you can do that, and then you can do this. And actually, that is how I am going to solve it, because I think it's a little bit easier that way. So let's start by finding our mass defect in AMUs. So our mass defect in AMUs is 2 times 1.00728 plus 1 times 1.00867 minus 3.01603. So my mass defect is going to be 0.007 U. But I need that to be in kilograms in order to use Einstein's equation, in order to use E equals mc squared. So I need to multiply that by 1.66 times 10 to the negative 27th to figure out the number of kilograms that I have. So that's the number of kilograms in one atomic mass unit. So that's going to give me an atomic mass defect of 1.162 times 10 to the negative 29th kilograms. Plugging that into my second equation, I get that the binding energy per nucleon is equal to 1.162 times 10 to the negative 29th times c squared, so 3 times 10 to the 8th quantity squared, divided by the number of protons plus the number of neutrons, or 3. So plugging that into my calculator, I will get that my binding energy per nucleon is 3.486 times 10 to the negative 13th joules, which is a tiny amount. But if you remember back to our previous unit, we know that 1 joule is equal to 6.242 times 10 to the 18th electron volts. So if you remember back to the first unit, we introduced a measurement of energy called the electron volt that I said was really helpful for small amounts of energy. Well, here's a great example of small amounts of energy that are perfect for measuring in electron volts instead of joules. So we're going to multiply our final answer by 6.24 times 10 to the 18th. And we'll find that our binding energy per nucleon is 2.2 mega electron volts, or 2.2 times 10 to the 6th electron volts. Either of these answers is acceptable. This one is, of course, much more elegant. So moving forward, let's talk about why binding energy per nucleon matters. So remember when we talked about nuclear decay, I showed you this graph. And if you look at this graph, you'll actually see that we are measuring the number of nucleons versus the average binding energy per nucleon in mega electron volts. So the higher our binding energy per nucleon, so as binding energy per nucleon increases, the stability of our atom also increases. The length of a half-life will increase, and the chance of decay will decrease. Additionally, we know that nuclei are only going to decay if the nucleus that they are turning into is a more stable nucleus. So what that means is that if we draw a line through iron 56 with our light nuclei to the left and our heavy nuclei to the right, remembering, of course, that iron 56 is our most stable nucleus, what we'll find is that everything to the left of iron 56 will decay only through nuclear fusion. So this is the fusion side. And that those to the right of iron 56 will decay only through fission. Additionally, this tells us iron 56 not going to decay. So no nuclear reactions are going to happen with iron 56. So with that, let's go ahead and move forward and talk about, okay, if we have nuclear fusion or nuclear fission happening, how can we calculate the energy that's released in that reaction? So what we're going to do is we'll calculate the total mass on the right-hand side of the equation. So if we have, A plus B turning into C, or A turning into B plus C, I'm going to start by calculating the energy on the right side of the equation. The mass of the right side of the equation. Then we'll calculate the mass of the left side of the equation. We'll subtract the mass of the right-hand side from the mass of the left-hand side. So we'll subtract 1 from 2 and use E equals mc, and that's going to give us, of course, our mass defect. And we can use E equals mc squared then to calculate the release energy. So let's look at an example. The unstable nuclide Na2411 is going to decay into 2412 magnesium. So sodium is going to decay. And we know that the rest mass of sodium 24 is 23 point, I'm not going to read the whole number, but you can see it there. We also know the rest mass of sodium. Excuse me, that should say magnesium, guys. That is my bad. And we know that is 23.98504 U. The energy released during the decay, so we know the energy released is 5 etc. mega electron volts. We need to figure out the mass of the particle emitted during this decay. So first of all, let's identify the particle emitted, since we have done that already. So we know it has to have a charge of -1, therefore it must be an electron. And of course we have the electron antineutrino. That has no mass, no charge, so we don't have to worry about it here. So we're going to start by figuring out the total mass of the right-hand side of the equation. So on the right-hand side, I have my magnesium, which has, so the mass of my magnesium is 23.98504 U. And that is going to get added to some sort of mystery mass, the mass of our electron. So that's to me the right-hand side. The left-hand side of our equation is the mass of sodium 24, so Mna, which is 23.99096 U, and that's the whole left-hand side of my equation. Now I know that the energy released is equal to the mass defect times C squared. But my energy released needs to be in joules, and my mass defect needs to be in kilograms. So let's go ahead and fix that up really quickly. So we can rewrite this equation. Before I do that though, I do want to just write my binding energy per nucleon equation, and that's going to be that that my binding energy, or my mass defect, excuse me, is 23.99096 minus 23.98504 plus the mass of my electron, which is a mystery. So what I can do is I can actually subtract these two from each other, as long as I remember to distribute the negative sign there before I do any unit conversions. And that's just going to give me what I'll find my mass in kilograms instead of my mass in AMU. So I can easily go back and forth if I need to. So anywho, skipping to the part where I do the subtraction, I'm going to subtract them, multiply by my conversion factor of 1.66 times 10 to the negative 27th. And what I'll get is that the mass defect is given by the equation 9.8272 times 10 to the negative 30th kilograms. And I can plug that now into E equals mc squared. 9.8272 times 10 to the negative 30th kilograms minus the mass of my electron in kilograms. And I know that that times c squared is equal to my energy in joules. So before I can plug my energy in, I do need to convert from mega electron volts to joules. My conversion factor there is going to be 1 mega electron volt is equal to 1.602 times 10 to the negative 13th joules. So doing that calculation, what I will get is that my energy release here is 8.01346 times 10 to the negative 13th joules. And that's going to equal c squared, or 3 times 10 to the 8th squared, times 9.8272 times 10 to the negative 30th minus the mass of my electron in kilograms. And from there, I can do some algebra to solve for my mass of my electrons. I'm going to start by dividing by 3 times 10 to the 8th squared which gives me that my mass, 9.8272 times 10 to the negative 30th minus the mass of my electron is equal to 8.9038 times 10 to the negative 30th, giving me that the mass of my electron is equal to 9.234 times 10 to the negative 31st kilograms, which if you look up in your data booklet is almost exactly the actual mass of an electron. So now that we've done these example problems, we can go ahead and talk takeaways. First, we can use mass defect to calculate binding energy, or binding energy per nucleon. Second, we can also use that to calculate, the energy released during a nuclear reaction. Secondly, we know that nuclei that are lighter than iron-56 decay through fusion, while nuclei that are heavier than iron-56 decay through fission, and that iron-56 does not undergo nuclear decay. With that, it is your turn to go out and try calculating binding energy per nucleon on your own. Best of luck, and happy solving.